So thank you very much for the introduction. It's an honor to be here, and I'm delighted to speak to you about artificial intelligence. I am not an ethicist by training, but so unlike the previous speaker, my take will be I'm coming from this as somebody who builds AI systems and who has studied AI systems for many years. So I'm going to share my screen now and get going. Can everyone see my screen?
Yes.
Okay, good. So artificial intelligence, promise and peril for humanity, sort of a dramatic title, sorry, perhaps overly so. Oops, move on, oh dear. There we go, okay, oops. So when I teach AI at the University of Toronto, often it's, this is the definition that I usually give, but many people debate how to define artificial intelligence. So artificial intelligence is the study of how to achieve intelligent behavior through computational means. It's a transformative technology that is changing the way we live and work. The rapid advances and impact AI is having have surprised even those of us who've actually worked in AI for many years. I think none of us would have forecast that we'd be where we are now 5 or 10 years ago. The change in AI and the speed of advancement has been just staggering. And a lot is happening in Toronto as well. As probably many of you know, University of Toronto is really one of the world leaders in the development of artificial intelligence. And these are just some screenshots of things that we've seen in the media, how Canada became a hotspot for AI research. Of course, University Professor Emeritus now, Jeffrey Hinton, in just down the hall from where I'm standing right now, developed the area of deep learning and did a lot of the fundamental work in machine learning that has led to this just amazing advance in AI. And some of there are many labs in Toronto, research labs by private industries, including, for example, Uber has a self-driving lab that is being run by one of my colleagues, Raquel Erdson, who's pictured there. There's a pan-Canadian AI strategy that has resulted in the creation of the Vector Institute in the Mars building at the corner of University and College that has gathered together many leaders in artificial intelligence research. And of course, most recently, Jerry Schwartz and Heather Reisman gave $100 million to donate to a new building at U of T. But part of what they did was, as this gift, was to create the Schwartz Reisman Center for Technology and Society, whose mandate in the short term is to study AI and the impact of AI on society. So where are we now? This image is one that I took from Nature Review, and it talks about, it characterizes the advancement or the progress of artificial intelligence as compared to human intelligence. And on the x-axis, the horizontal axis is time, and on the vertical axis is performance or intelligence of performance. And you can see we're right in the middle right now. I don't know whether you can see my cursor, but we're at the point where, I don't know whether I agree with this exactly. Maybe I think we're maybe a little bit over here, where certainly where we are right now is that AI we are able to build AI systems that perform or outperform humans on very siloed tasks, on language translation, on speech recognition, on interpretation of mammograms or interpretation of MRIs. We can build AI systems that are as good as or superior to human performance. But what we can't do is stick them all together to create a superhuman or a human who can do all of those things, just as we can. And so we've got a ways to go toward before we get to the right quadrant. So sorry, just I wanted to highlight a few of the areas where AI is really operational right now or making extreme advances. So self-driving cars, we hear a lot about it. And of course, a quote down in the right-hand corner, weather is tricky. And in particular, if you look out the window and imagine you're a self-driving car, the weather is tricky today, but it is the case that in more temperate climates like Phoenix, that Lyft and Waymo, you are able to take a taxi or a minivan that is a self-driving vehicle. In Texas, Kroger is delivering groceries to people using self-driving cars, and in Florida, Voyage is also using self-driving car technology. Of course, you know, the problem, these are in very nice restricted circumstances, but self-driving cars are coming. Another really impressive technology that results from AI, and I don't know whether you've seen this, is this real-time language translation. So if you look at these two images of the phones on the left, if you take a picture of a sign, for example, in a particular language, in real time, you can get it translated into another language. And furthermore, we can also record our spoken language and have it simultaneously translated into a number of different languages. This is technology that's still evolving, but it's incredibly impressive, and it's being realized through advances in artificial intelligence. For those of you who are, you know, we're all locked away in our home, and I know many people are actually doing online shopping. And of course, if you're buying something from Amazon, for example, many of the fulfillment, or all of the Amazon and other grocery store and big box fulfillment centers are actually operated using robotics. What you're seeing in the video that I'm showing right now are these little orange pod robots. This is actually about 10 years old, I think, this video, where the pods actually go. I'll just pause this. These pods go, they have different racks with different items for sale in them, and the robots are able to software is able to look at an order, find the racks that contain the objects that are in the order, and bring those to, drill underneath the rack, lift up the rack, and bring the rack to somebody who fills the order. And of course, as I showed, there's a real driving task associated with this. Just a second to try to get the robots, make sure that none of the robots smash into each other as they're navigating the hallways. And of course, another incredible advance of artificial intelligence is in the interpretation of mammograms, skin cancer image analysis, and MRI interpretation, any sort of radiology task, because what computers are really good at, and what AI is really good at, is recognizing complex patterns in large amounts of data and doing so consistently 24/7. And we're seeing that in advances in medical diagnosis in this particular setting, but you know, there's much more to come. So in addition to these sort of perceptual tasks, AI is also making leaps and bounds in terms of more deliberative tasks. And one of the best publicized examples of that was the game of Go, which of course is a board game with 400 pieces, where the players have to, it's a very popular game in Asia. And of course, for those of you who heard about this, Google DeepMind, which was actually an Alphabet company, had researchers who built a game of Go that actually outperformed the 9-Dan Go player, Lee Sedol, in beating him in 4 out of 5 games. And this was just unthought of, because it's such a difficult game. And unlike chess, where there are chess endgames and you can actually recognize progress towards winning, it's very hard to look at the board and figure out how to, you know, who's winning and who's losing and what the strategies are. So I can talk a little bit more about how this worked if anyone's interested, but that's not sort of the topic of this talk. So AI is in everything, and it's everywhere, from toasters to Teslas. And of course, part of that, you know, when you hear that, you read that in the newspaper, or we're all victims to that in big box advertising. But of course, with the proliferation of sensors and with the ability to collect data, the opportunity for integrating data science and data-based AI is really becoming pervasive. And of course, in some cases, it's quite innocuous. If AI is being used to get your bagel to exactly the right color or the right toast level that you like, that's great. But AI is also being used to make other forms of decisions, to filter through applications for jobs, or to decide on mortgages or other types of decision-making tasks. And that's where I think, some of these ethical issues that are associated with AI arise. Advances in AI will have a significant impact on society, and AI introduces a lot of ethical challenges. For developers like me, people who build AI systems, we need to understand how we can develop AI to do the right thing, to make decisions that are aligned with human values. And for people who are deploying AI, for people who are building systems, they need to understand how to ensure that the systems that we are building are developed in a manner that protects human rights, that protects our data, that protects our privacy, that protects our liberty, and that are deployed for the good of humankind and not, for example, as tools of oppression. And so there's some really, there are challenges for all of us in terms of along multiple different dimensions and making sure that AI is developed and deployed, because it can give so much to society like CRISPR, but also with many caveats. So one of the problems I think in addressing this problem is understanding exactly what the right thing is. And if I talk to my colleagues who are not computer scientists, but who are philosophers or social scientists or economists, we all use these words, but we often mean very different things from them. So we want our AI to be fair, equitable, moral, unbiased, rational, principled, transparent. So I created this Desiderata for decision makers of a list of things that we want our AI system, our AI decision-making systems to be able to attain. Maybe not all of them are necessary in all circumstances, but I think they're a pretty good laundry list of concerns, ethical concerns, or issues that relate to ethical concerns associated with artificial intelligence. Fairness, bias, transparency, interpretability, explainability or accountability, that any decision maker is audible or verifiable, controllable and modifiable, privacy preserving, trust inspiring, and most importantly, safe for humanity. So an interesting question when you contemplate the development of AI systems is what we should expect of those AI systems. Should we expect it? Humans are fallible and we do all sorts of jobs in our life. Should we expect our AI to do as well as us? Should we hold it to a higher level? I have a teenage daughter who got her driver's license a little while ago, and she's a good driver, but she's not as good a driver as me. But I have supreme confidence in her. She's actually a very responsible teenager. But there's a question about whether we will hold our AI to higher standards than we hold ourselves. A funny quip that one of my colleagues observed was that close to 3,000 people are killed in motor vehicle accidents in Canada each year, more than 10 times that many in the United States. If automated vehicles or self-driving cars cut that in half, do you think the manufacturer will see 1,500 thank you notes? Probably not. More likely that they'll receive 1,500 lawsuits. So there's an interesting question about, even if we are able to improve on certain services using AI, will we give them the same buy that we do to our human colleagues? So in order to understand some of the ethical concerns associated with AI, I think it's really important to sort of peek under the hood and understand what we mean by AI and how it works, so that you can, because I think the devil is in the details. Appreciation of some of the concerns is really related to how AI works. So, for some people, I think it's a little bit puzzling. We've been building safety critical systems for a long time. We have computers that control nuclear power plants, computer systems that control the traffic lights that if they failed would be disastrous. And all of our cars nowadays have anti-lock braking systems that take control of the braking system for us. We have autopilots on our airplanes that if they failed would be disastrous. So what's different about AI and why all of this concern? So one of the differences is that most of these systems that I've described here are able to be modeled. Human beings can construct a mathematical model of the behavior that we want, the operation of the system, and understand or circumscribe the environment in which it's going to be used and the things that might happen to it. So how hard is it to build these models? You know, amusingly, sometimes it's actually, you think about going to flying to the moon and what an amazing feat that is for humankind to have achieved. But you know, we understand the physics. We understand the physics of sending a plane to, or a spaceship to the moon. It's just a parabola. There's no traffic, and it's quite easy. Whereas something as simple as walking down the street, as depicted here, can be incredibly difficult to model and incredibly difficult to actually realize and build into a system. And it speaks to, you know, our ability as human beings that we're able to do this. So when we don't have models, or we can't actually construct models, what we want to do is we try to learn models from data. We try to learn models from our experience, and we try to figure out how to act directly given that data, perhaps via deep learning. So what I want to talk about now, many of you have probably heard about deep learning, or what's referred to as modern AI, machine learning and deep learning. So AI, previously we would build these complex models, and now what we're doing increasingly is trying to create AI from data and from experience, sometimes with some models, but we recognize the limitations of even the models that we're able to build. And this evolution has come about not only because we understand how to do machine learning, but also through two game changers, the prevalence of sensors and labeled data that allows us to be able to learn, and also huge advances in computational machinery, and in particular GPUs, graphic processing units, that we're able to use to do huge numbers of computations very, very quickly in order to mobilize machine learning and deep learning. So this is a picture of a deep neural network. It takes a set of inputs, x1, x2, x3, x4, and produces a set of outputs, y1, y2, y3. And the challenge is to learn a mathematical function that actually does the type of mapping that we want. So just to ground that, if I had a bunch of pictures of different dogs, and they were all labeled, this is a Boston Terrier, this is a poodle, I had 50 or 100 pictures of Boston Terriers, 100 pictures of poodles, 1,000 pictures of Dalmatians, and so on and so forth. And I took those images and took the pixels, you know, the color of each of the dots of that pixelated image, a huge set of input vectors, and I fed it into a neural network. What I'd want that neural network to do is to output a set of bits at the end with a weighting for which thing I thought was most likely. Gee, you know, 95% it's a Boston Terrier, and maybe 3% it's a Dalmatian, 4% it's a 2% it's a bulldog, and so on. So to do deep learning, what we have to do is learn that function. And I'm sure many of you are familiar with this is simple mathematics that I do with my kids. You know, this is a simple function, y equals mx plus b. You put in the x's, and you can predict the values of the y. And we have parameters that define this line, the slope of the line, which is 3, and the intercept with the axis. So that's a function, that's an example of a simple function. So if we have a bunch of data points like these black dots, then we can jiggle our line up and down to sort of figure out the right equation that we want that minimizes the distance between any of the line. It minimizes something. It minimizes the error in the prediction of that function. And what we typically do is we minimize the squared error of the distance between each of these points and the line. And of course, that creates a predictive classifier for us. We can use all sorts of different functions that may be more accurate. I can create a function that actually perfectly captures all of the data. But of course, this overfits to the data. And then it becomes the case that if I have a new dot, it's not going to be able to assess it very accurately, because the function is overfit to the data we have, and it's not going to be very good at predicting other data because it's such a complex function. So this is what we want to do this is what deep learning does. what deep learning does is it gives a set of examples and then it produces an output, and the output says, hey, you said that was a poodle, that's not a poodle, and it propagates the error back, and it goes back and forth along this network, training with millions and millions of pieces of data with huge number of inputs in order to construct a function that will map those inputs into that output. And it's called deep learning because there are many layers to this network that create this very deep network that captures, interestingly, as we visualize, all of the different components that create a particular recognition system. So this is an example here that you're seeing on your screen of an input of a particular person named Sarah. And somebody has actually visualized what we see in each of the different network, and each of the different layers of the neural network. And what we can see emerging is these different features or building blocks of Sarah's face or the many other faces that are being classified with this deep neural network. And it's actually quite fascinating to visualize some of these things. So there are many different forms of, or there are many different forms of machine learning algorithms, but there are three sort of prevailing types of machine learning algorithms that people talk about. One is supervised learning, where we take a set of labeled data like the Boston Terriers and the poodles and so on, and we train a model so that it can recognize, in this case, instead of dogs, apples or bananas. A different type of learning is unsupervised learning, where we just take a set of objects and we try to recognize the different pieces. We try to cluster them into groups that are similar to each other and without being able to label them. And a third form is something called reinforcement learning, where we actually are trying to, an agent interacts with an environment and tries to learn how to act in that environment. Given to maximize their cumulative reward. So imagine closing your eyes and being placed into a room and trying to find the door. You have nothing but your ability to walk around and feel, and you get positive reward for hitting a wall, for touching a wall, and negative reward for bumping your feet into a piece of furniture. And over time, with experience, you figure out how to get out the door. This is the type of learning that these systems do. So deep learning really revolutionized computer vision. Computer vision, we've been able to do some form of computer vision for tens and tens of years, but as you can see from this graph, the level of accuracy of computer vision systems on this sort of classic benchmark data set that was used to evaluate the efficacy of computer vision systems was around 70%. And then when deep learning came along in 2012, it moved up and up and up and just really made old computer vision systems that were based on physics and optics and mathematics and as we as human beings understand computer vision, it really made them nearly obsolete. So as impressive as AI's performance is, there remain serious challenges to its broad deployment. And in particular, here is an example here that I've depicted. So this a deep learning system that was, had the very high accuracy that we saw, said that this image was 75% a panda. And then if we add arbitrary noise, imperceptible to us human beings, to the image, to create this image on the right, which looks exactly like the panda on the left to me, what the deep learning system said was that it was 99% sure it's a gibbon. And of course, that's completely wrong. So even though this system was doing well on predicting data, when we add random noise to the images, the system is doing poorly. These are adversarial examples, but it shows that perhaps our systems are more fragile than we think, and they're not working for the reasons that we think that they're working, even though they're working so well. And that to me is scary. So what would it take for us to trust our AI? How can we verify it's doing the right thing? And for what we might consider to be the right reasons. And I think researchers in AI are asking themselves, like, can we use these deep learning systems and understand how to generate explanations for them. So can we get our AI to explain its thinking, the rationale behind its decision making? The answer is maybe. If it's following a human interpretable recipe, like then maybe we can do that. But like humans, AI may become very good at providing post hoc rationalizations instead. So if you think about it, if I recognize Daphne when I see her, but if you ask me to explain why I recognize her, I might give you some explanation about her haircut or something else the last time I saw her, but it's very hard for us to articulate, especially with respect to perceptual tasks, why we believe somebody is Daphne and not Margaret, or so on. So it's even hard for us to articulate those things. So it's hard to imagine that in all cases we're going to be able to build AI systems that are going to be able to give us explanations that are really faithful to the reasoning, just as human beings cannot do that. Interestingly, this was—
Sheila, excuse me, this is Daphne giving you a 5-minute warning.
Yes, thank you. I'll have to speed up a little bit. So this is an example of a task where that AI had great difficulty with. It was trying to it was trying to distinguish between huskies and wolves. This was a husky that it predicted to be a wolf. This was a husky that it predicted to be a husky. And this was a wolf that it predicted to be a wolf. And when we did try to build explanation systems for it, we realized that what was happening was that the AI system wasn't looking at whether it was a husky or the features of the facial features of the husky or the wolf, which is what we would think it should be doing, but rather it was looking at the snow in the background. And it turned out that a husky on the left is confused with a wolf because the pixels on the right characterizing the wolves are the snow pictures that are being used rather than any sort of discriminating properties of facial features. So we're learning how to recognize where our neural networks are attending to particular properties, and that's helping us. In addition to the algorithms, AI is only as good as the data it's trained on, and I think that this is a really important property to appreciate. In particular, if we have biased training data, then the classifier, the decision maker that we're going to construct is going to be biased as well. Similarly, if an object, a picture, or an ill patient is out of distribution, you give the system a picture of a cat and it's only been trained on dogs, or you give the medical diagnosis system a female patient when it's only been trained on male patients, so therefore it's out of distribution, then the classifier decision maker will not be effective. And this is really important, not just for the things that we recognize and predict, but understanding that our data is really representing the distribution of problems that we wanted to solve, and doing so in an unbiased manner. So there were two very interesting examples of this that I wanted to bring up. Amazon in 2016 decided that it wanted to create an automated recruiting tool using AI. So it took all of its old CVs for people who had applied for jobs and all of the decisions it had made, and the assessments of people after they'd been hired, and it created an automated system that learned from that data. And that system was incredibly shown to be biased and incredibly biased against women. And they tried to fix it and they couldn't, and eventually just withdrew the system. Now, of course, though that data was the data that reflected what Amazon's practices were, so it actually uncovered a bias that existed within Amazon, which is a good thing. But of course, if that tool had not been scrutinized, that practice would have been automated and continued. Similarly, there's a very well-known case of trying to use to help judges with cases of deciding on bail, whether somebody should get bail or whether somebody should get bail and be released, or whether they should go to jail. And one of the predictors of that is recidivism, whether the person is likely to offend again. And again, a system was built using historical data based on judges' decisions, and it was found to be incredibly biased The good news is that it's subsequently been fixed. But again, this shone a spotlight on the problems related to algorithmic bias, problems with data, and the vulnerabilities that we have with using AI systems. So AI is good in that it enables us to expose bias, but it also can systematize and automate that bias and make it more pervasive and broadly available. It isn't just the algorithms or the models or the data, and I know I'm at 30 minutes. I'm about 3 minutes away from being done. So I just also wanted to mention that another problem that we have is in reinforcement learning, where we're trying to decide how to act given signals from the environment. And in this particular case, we've all heard the headlines, should the driverless car kill the kid or kill the retiree? What we want to build AI systems to do is we want to build our AI systems to align with our human values, and we want them to be able to act in accordance with user intents. And the problem is that if we don't mention a particular attribute of desirable behavior to our AI system, it will optimize for something else. So if I go and ask my AI system to go and get me a coffee at Starbucks, it will be tasked with optimizing that task and doing it as well as it can. And what it could do, if not trained to otherwise have the values that we have, that it could blast into Starbucks and run over everybody in line in front of it with the strong intention of fulfilling my request for it to get coffee for me, harming people en route. And so that's a dramatic example, but I guess but it illustrates this idea that if we don't tell our AI systems what we want them to do, they will vary and change things in order to optimize for the task at hand that they are trying to optimize for. And what our systems really need is some form of common sense and some form of humanity. AI systems should be designed so that their goals and behaviors can be assured to align with human values throughout their operation. So how do we ensure AI is used for good of humanity? Again, I'm sure all of you or many of you have heard about the abuse of facial recognition systems in China to monitor and control people's behavior. This is just one of the examples of how AI is used to oppress people, or has the capacity to be used to oppress people. I guess the good news is that there are many organizations that are looking into this, that are looking into regulating AI, looking into understanding how AI should be delivered and controlled. Microsoft, for example, has an ethics body that actually has not released certain software because they didn't feel comfortable that it could address its corporate values with respect to delivering ethical software that was not open to abusing human rights. And so here at the University of Toronto, I believe that one of the ways that we can solve the problem or address the problem is through education. And I'm involved in an embedded ethics program within the computer science department that is trying to train our young people to think more broadly about privacy issues and issues concerning the broader impact of the software that they are building, and how to design it in a way that that preserves our humanity and is good for society. And I believe that if we if we educate our students who are building these systems, and that if they go out into society and work at all of these companies, that this will be the best way one very effective way of addressing this problem. And I can tell you a little bit more about that program afterwards. Wrapping up, I wanted to say that a wise friend with a good sense of humor once said to me, we don't need to replicate human intelligence in AI systems. We know how to replicate human intelligence. They're called babies. The problem is they'd have only human intelligence with all its limitations. And what I think we want to aspire to do is to build machines that complement our intelligence and support us in what we're trying to achieve. So thank you for listening. These are a few books, popular press books that I think are very interesting, some of which, except for the Book of Why, which is about causality, address some of these issues. And I will now cede the floor and stop sharing my screen so that I can take some questions. And